Hello, my name is Shaya Lopez, and this is my Lab 4 about oscillations for Physics 2211 with Dr. Yonker. So the purpose of this lab is to investigate and model the oscillating motion of a mass attached to a spring. So it's a spring mass system. We will compare an experimental and computational model in order to gain a better understanding of Newton's second law, Hooke's law, and the energy principle. We will use Tracker to track the observed position, as well as GlowScript for the computational model to graph motion and energy changes. The fundamental principles that we need to know for this lab is Newton's second law, which pretty much states how the systems change in momentum proportional to the net force applied, as well as the energy principle, especially that the change in energy is equal to the work done by the surroundings by Q, which is the thermal energy exchange with the surroundings. We also need to know Hooke's law, as well as the position and update formula and the velocity update formula. So the setup of the experiment, we have as the system, we have the spring and the mass, as well as the earth, in order to have nothing in the surroundings. The initial conditions that we have is that the position is negative 0.118 in the x direction, negative 0.616 in the y direction, and 0 in the z direction. Our initial velocity is 0 meters per second, and the mass is 0.402 kilograms. Here we can see the video of the tracker and the movement within the dot stated, and here is the graph that we get for the mass in the x as well as in the y values. So for the computational, what we did was in GlowScript, we used the code that was given to us and we edited. So we put the ball mass, the position as well as the velocity, here the gravity, the spring constant, the relaxed length of the spring. Also, we added the formulas to find L as well as L hat in order to find S, as well as the kinetic energy, the gravitational potential as well as the gravitational spring energy, and then the total energy, which is the sum of all of these energies combined. Then we defined our initial energies. We calculated the gravitational force, as well as the spring force and mass by spring. We also calculated the net force. And in here is where we used Newton's second law in order to update the ball's velocity as well as its position, and then update the spring in order to calculate the final energy changes. So here in the video, we can see the experimental graphs that we get, from the computational graphs that we get from this code. This R is in the X direction and here in the Y position. Okay, so now comparing the two that we got, the experimental versus the computational. So the similarities that we have in the experimental, that there are similar periods of oscillation and overall shape of the graph is similar. The difference is that it predicts larger maximum and minimum values of the y direction. So in conclusion for this one, we have that the different values for the maximum and minimum could be because of possible overestimation in the initial displacement. Now for this other one, the similarities that we have, we see that there are similar periods of oscillation, shape, and amplitude at first. The differences is that deviation of the model intensifies as time goes on. And as a conclusion, we can say that the graphs deviate more as time increases because the spring constant was calculated with average values, which are not the most accurate. So these are the similarities and differences these two graphs have with the experimental ones that we had before. So our sources of error, the human error, as well as the GlowScript and Tracker miscues, as well as the surrounding forces, because the friction and drag were not accounted for. As a conclusion, as follow-up, so for your model system, is the energy principle satisfied? Yes, in this model, the energy principle is satisfied because although there are various forces present, the sum of all of them is equal to 0. And this means that as time passes by, the sum and the delta, the change in energy will be 0. And this is due to how we choose the system and surroundings, as we left nothing in the surroundings, so it will always be equal to 0.